This video is in conjunction with homework 7-4, and this has to do with sampling distribution of the sample mean. So this is page 2. If you look, we have page 1 here, page 2. So on page 1, you were doing sampling distribution for sample proportion, and now I'm going to introduce the sampling distribution of the sample mean. So it says, the scores of individual students on the ACT is normally distributed with a mean of 18.6 and a standard deviation of 5.9. Notice I'm going to circle that, and I'm going to circle the word normal, and I'm going to write mu, comma, sigma, and I'm going to write 18.6 and 5.9. Okay. Now it says, what's the probability that a single student, so one single person, will score 21 or higher? So this is actually a chapter 2 question, and I'm hoping that you were thinking, oh, I'm going to do the probability that x is greater than 21. I'm going to draw my bell curve. In the middle, I'm going to put my mean, 18.6, and then I'm going to shade to the right of x equals 21, and I'm going to do normal CDF or the z-score. So I'm going to show you both. So if I did normal CDF, my lower bound would be 21. My upper bound is going to be infinity. My mean is going to be 18.6. My standard deviation is going to be 5.9. I'm going to get my answer for my probability. So I get 0.342. Okay, that is the answer for the probability. Now I could also have done the z-score corresponding to 21. So if I did it that way, I would do 21 minus 18.6 divided by the standard deviation 5.9. I would get my z-score, and then I would go to table A. So let me show you that. So we get a z-score of 0.41. And then I'm going to go to my table A, and I'm going to get my. So if you look on table A and you look at the z-score of 0.41, you get 0.6591. And remember, that's this area to the left. So you have to do 1 minus 0.6591 to get the area to the right. I get 0.3409. Notice that's pretty close to what I got for my answer over here. I got 0.342 for normal CDF, and here I got 0.341, so pretty close. So this is review from chapter 2. Now, how is this one different? It says an SRS of 50 students, so let's circle that. That's the sample size N is taken. And what is the probability that the mean of those 50 is 21 or higher? So now, instead of finding the probability of a single individual student score being greater than 21, as we did in part A, we're actually looking for the mean of those 50. So the first thing is, this is a sample. It's an SRS. So the mean of that sample is going to be called X bar. Okay, so that is a statistic because it comes from a sample, and specifically that is called the sample mean. So a quick recap of our symbol. If we're talking about a sample versus a population, if we're talking about proportions, then we're going to use p hat and p, where p hat is the sample statistic and p is the population parameter. But if we're talking about means, we're not going to use p and p hat because we're talking about means. So we're instead going to use x bar if it's a sample, and we're going to use mu if it's a population. And the x bar should estimate the population mu. So keep in mind there's going to be a shift in symbols. So now I'm actually looking for the probability x bar, which is the sample mean, because it says the mean of the sample of 50 students is going to be greater than 21. So now let me ask you this. Do you think that it is going to be more likely or less likely that a mean of 21 students, a mean of 50 students is going to be greater than 21 versus a mean of a single student? The probability of a single student having a score of greater than 21 is 34.2% of the time. So do you think now if we made a sample of 50 students, do you think it's going to be more likely or less likely that if we took 50 and we found the mean of those 50, that the mean of those 50 would be greater than 21? Okay, so think about that. I'm hoping you're going to say it's probably going to be less likely. And hopefully you're thinking about the reason why it's less likely is because when we're dealing with averages, the average of 50 students is probably, it's going to be rarer that that average is going to be more to the right. Because when we're doing averages, we're finding the mean of something and it's going to be more in the middle, not more to the right. So this is probably going to be less likely than the above example. Okay, so we are going to set up the bell curve for the X bar, but before we do, we have to go through all the things that we did for the sampling distribution of P hat with the sampling distribution of X bar. So down below, we're going to come back to this question. We want to review that the sampling distribution of a statistic is all the possible samples, in this case, all the possible values of the sample statistic, which is the sample mean in this case, X bar, taken or calculated from samples of the same size from the same population. Same size N, which in this case is 30, from the same population. And they're random samples, by the way. Okay, so whereas before we were taking a sample, finding the P hat. Take a sample, find the P hat. Take a sample, find the P hat. Now we're taking a random sample and we're going to find the mean. Take a sample, find the mean. Take a sample, find the mean. Take a sample, find the mean. And that actually was this applet here that I had shown you guys the other day, where you take a population, you take a sample, and then you find the mean and you plot the mean. Take a sample, find the mean, plot the mean, take a sample, find the mean. And then what's going to happen if we did this many times, the sampling distribution of the sample mean should be approximately normal in shape. It should be centered at the true value of the parameter, which makes it unbiased, and it should be less spread out than the overall population. So that is what we're going to see down here. So remember with the sampling distribution of the P hat, we had to go to the reference sheet for the measures of center, the measures of spread, and we had to do some rules of thumb. Similarly here, we're going to look at center and spread for X bar, okay? So the measure of center is going to be the mean. If you do the mean of all the X bars, it should equal the true parameter, the true mean of the population. And that formula is located on the reference sheet. So let me show you where it's going to be located. So here is my P hat on the top here. It says proportions, sampling distribution of proportions. We were just doing center and spread here for P hat. Now we're just going to look down here at means, and we're going to look specifically at center and spread. Okay, so mu sub X bar should equal mu, that's center. And sigma X bar will equal sigma divided by the square root of n, that's spread. Okay, so I'm going to use these two formulas now on the page here. So the standard deviation is sigma divided by the square root of n, where n is the sample size. Now think about this. The sample size is in the denominator, okay? So going back to my question that I just asked you, in part A, the sample was size 1. It was only one student, and we found the standard deviation was 5.9, right? So now I'm going to have a sample of 50 students. The n is going to be 50. So if you look down here, since n is going to be in the denominator, if I take that 5.9 and I divide by the square root of 50, which is the sample size, is that standard deviation going to go up or down? I'm hoping that you're going to say the standard deviation is going to go down. So if you do 5.9 divided by the square root of 50, you're going to get 0.834. It's way smaller standard deviation. The overall population standard deviation was 5.9. So remember back to my applet that I just showed you guys. In the applet, the standard deviation of this sampling distribution is way less spread out than the standard deviation of the population, because we're finding the means, finding the means, finding the means. So less spread out than the population, which is what we said. And this says the center is centered at the true parameter value. And then also look at this, we have our condition here. So we're not allowed to use the formula for standard deviation, again, unless that 10% condition is satisfied. If that is satisfied, we're allowed to use the standard deviation formula. Okay, and then the last thing to note is that we're not allowed to assume that the sampling distribution is normally distributed unless there are two things that could happen. If the overall population is stated to be normal, then the sampling distribution will also be normal. Specifically, it will be approximately normal. So that's one way to do it if they tell me the overall population is normal. Or the sample size will have to be large enough that overall the values of the sampling distribution will become more and more approximately normal. This is called the central limit theorem, or CLT for short. Basically what it says is if n is large, how large? It depends on which textbook you read. Some say n is greater than 25 is sufficient. Some say n is greater than 30 is sufficient. Then the sampling distribution of x bar will be approximately normal. Now, you're probably thinking, well, this is a different rule than we did in the p-hats. And you're right, because with the p-hat rule, for p-hats, we did NP and NQ have to be greater than or equal to 10 for it to be approximately normal, right? But remember, we don't have p, so how are we going to do NP and NQ if we're talking about means? We can't do it for means. So we have to do a different rule of thumb for this, okay? So the last thing we're going to do is answer this question. The question that I asked above, I'm going to answer it again. So just a reminder, the population mean was 18.6 and the population standard deviation was 5.9. And it said we're taking a sample of 50 students and we want to know the probability P that the mean of the 50, that's called X bar, of the sample, so sample mean, will be greater than 21. 21 or higher, sorry, at least 21, okay? So basically, I'm not allowed to assume that it's going to be approximately normal yet, unless I know that the sample size is large enough. So since the sample was size 50, indeed, that number is large enough that it will be approximately normal. So the first thing I want to address is shape. The shape of the sampling distribution will be approximately normal because by the central limit theorem, which I'm going to write CLT for short, since n, which is the sample size, is equal to 50, which is greater than 25 or 30, the sampling distribution will be approximately normal, okay? So that's a large enough sample size for it to become approximately normal, the sampling distribution of X bar. Nice, so that's done. Now let's do mu sub X bar, center. The center will be centered at the true parameter. Mu sub X bar will equal mu. So the mean of the population was 18.6, so this will also be centered at 18.6. Nice. And now we're going to locate 21. Boom, it's going to be to the right. And we're going to label it X bar instead of P hat. We're going to put 21, and we're going to shade to the right. Now, remember, if we're going to do a z-score, we're going to need the standard deviation. If we're going to use normal CDF, we're going to need to do the standard deviation. So the spread is the last piece of the puzzle. Spread is the formula that I had above. Sigma X bar equals sigma divided by square root of n. So we did it above. We did 5.9 divided by radical 50. And if you remember, we got a number that was much smaller than 5.9. We got 0.834. Okay, so that's going to be the spread, smaller than the overall population. So now we're ready to find the probability. There are two ways that we forgot, we have to check the rule of thumb. Sorry, 10% rule. Before we did that formula, we should have checked that 10 times n is less than the population of interest. So n was 50, 10 times 50 equals 500. Is that less than the population of all ACT takers? I'm sure it is. That's definitely met. So then we were allowed to use this formula here for spread, which we did. All right, so now we're going to do this two ways. We're going to use normal CDF and we're also going to do the z-score. First, we'll start with normal CDF. Second vars, 2, normal CDF. Now the lower bound is still 21. The upper bound is still infinity. The mean is still 18.6, but now the standard deviation is really changed because it's actually 5.9 divided by radical 50, which is 0.834. So the standard deviation went way down. And since the standard deviation went way down, let's see what happens to the probability. Oh, the probability went way down. Now it's only 0.002, which is the answer to this question. So look at what it was before. If you go back in part A, my probability before was 0.342, or 34.2% of the time, we're going to randomly select a student who's going to get a score that's greater than 21. But now, as soon as I incorporate 50 kids into my sample, it probably went way down that the mean of those 50 kids will be greater than 21. It's less than 1% of the time. Less than 1% of the time, this will occur. The sample mean of the 50 students will be greater than 21. Okay, so basically what this is saying is, as the sample size grows, you know what's going to happen to the standard deviation? It's going to go down. As n increases, standard deviation decreases. As standard deviation decreases, this curve is actually going to get narrower and taller. So whereas before maybe it looked like this, now it's going to get narrower and taller and less spread out, which is what we said in our little applet. And when it gets narrower, basically that tail that we had before, which was here at 21, if you write the same 21, look at the tail if it were just one kid versus the mean of 50 kids. That tail is way smaller. The probability is way down, okay? So I could have done this using z-scores as well. I'm just going to show you that briefly. Instead of doing x minus mu over sigma, or p hat minus mu p hat over sigma p hat, we're going to do x bar minus mu x bar over sigma x bar. So the x bar was 21. The mean was 18.6, and the standard deviation was 0.834. Okay, we would get our z-score, which this was sigma divided by radical n, by the way. That's where that came from. And then we would find the area. That's it.